Hi, my name is Olivia and my project is on differentiating sounds. Have you ever wondered how we can tell the difference between sounds or different instruments for that matter? For example, how can we tell that a saxophone is playing and not a clarinet or a guitar? This is one of the main questions that I was looking to answer when I started this project. So, the difference of sounds has to do with timbre, which is a musical term for the quality of a note or a sound, and it has to do with the presence of overtones of a fundamental frequency and the intensity of those overtones. So to explain an overtone, you can think of this graph, the red line, as a string on a guitar. And overtones are going to be the integer multiples of the fundamental frequency that the string is tuned to. So you have different allowed vibrational frequencies on this string. And because this string is what we call a closed system, there have to be two nodes at each end of the string. So when you start adding multiples of these frequencies, you're going to get different integer multiples. So if you have a frequency of 110 hertz, the overtones of that frequency are going to be 220, 330, 440, and so on. And when you start adding all of these different frequencies, which are vibrating on the string at the same time as the fundamental frequency, it will look something like this. And you're going to get a more complex waveform than just a perfect sinusoidal wave. Since a guitar string has more than just three overtones, or two overtones and a fundamental frequency, you're going to get many different overtones, and they're going to add up, and they're going to start to look something like this. So all of the different amplitudes of these overtones are going to contribute to the waveform at the bottom in black. And this is how you get more complex waveforms than just perfect sinusoidal waves. So to analyze timbre, you can record a note and plot the spectra of that note. And what this does is it essentially performs a Fourier transform on that waveform, and it's going to break it down into all of the perfect sinusoidal waves that exist in that wave. And it's going to give you the amplitude of each note, it's going to give you the amplitude of each frequency. And so I did this using acoustic, classical, and electric guitars to show the difference of timbre between those three types of guitars. Even though they're all guitars and they're very similar, they're very different in how they sound, and you can imagine that for different instruments, the waveforms are going to look quite different. So for the three guitars that I used a Yamaha APX 500 for the acoustic guitar, a Almanza Cedra 401 for the classical guitar, and an Epiphone Les Paul standard for the electric guitar. So the acoustic guitar has all steel strings, the classical guitar has 3 steel and 3 nylon strings, and the electric guitar has thinner steel strings, but they're still all steel. However, the electric guitar doesn't have any depth to its body, so it's very quiet by itself, which is why we have to play it with an amp or something to amplify the sound. The acoustic and classical guitars both have depth to their bodies, and they have this cavity, but the cavity of the acoustic guitar is quite a bit thinner. It has less depth than the classical guitar, so it's a little bit quieter as well. The classical guitar, since it has such a big cavity, has a lot of space for sound to resonate inside, making it a very loud instrument by itself. And all of these guitars are made mostly of mahogany, which provides a warm sound. And the acoustic guitar also has some spruce, and the classical has some rosewood, which both produce a bit more of a warmer sound. So what I did is I recorded the notes A, G, and E on each of these guitars. And to show you kind of what that sounds like, on the acoustic guitar, the A sounds like this, the G, and the E. For the classical guitar, the notes are going to sound like this. For the A, the G, and the E. By itself, it's already quite a bit louder than the acoustic guitar, which makes sense because it has a bigger body. And then lastly, for the electric guitar, the notes are going to sound like this. The A, the G, and the E. So it's very quiet by itself, which is why I always have to play this plugged into a speaker or an amp. And you can already see that the waveforms of each of these guitars are pretty different. comparing the A notes, the G notes, and the E notes. So when we take the spectra of each of these, so we'll start with the A. Basically what this is doing is it's breaking down those waveforms into each of the perfect sinusoidal waves, which are going to be the overtones of the fundamental frequency. So you can see that the first large peak is the A at 110 hertz. The spectra for these waveforms are already quite different, even though it's the same note, but it's being played on 3 different guitars. So for the acoustic guitar, you get a large peak at the 110 hertz, and you can see each of the overtones at 220, 330, 440, and so on, which are the integer multiples of the fundamental frequency. At the beginning of the classical graph, you can see that there's quite a bit more intensity, even though these aren't part of the overtones. And this has to do with the fact that the classical guitar has a lot more resonance by itself. And if you graph all of these harmonics and their intensities, you can see that the trends are quite different for each of them. For the G, the classical guitar actually has quite a bit more intensity, and it has some different peaks compared to the A. And this, I think, is because the resonance of the classical guitar itself is around a G. So the natural resonance of the body of the classical guitar is around a G frequency for any G, so G1, G2, G3. And so it gives these other bumps at the beginning. And you also get a lot more distinguished harmonics for the electric guitar because the higher frequencies are going to carry less energy. So all of the energy is being contributed just to the harmonics and not to any other sound. Then if you take the intensities of these spectra, you can see that the trends are also very different. The classical guitar actually has a louder second harmonic than the fundamental frequency, which again I think has to do with the fact that its resonance is around a G. And then if you do this, lastly for the E note that I recorded, you can still see that large resonance on the classical guitar and a lot more distinguished harmonics for each of the notes because again, the higher frequencies carry less energy, so more of that energy is going into just exciting the harmonics. And the electric guitar also has a very low resonance in the initial portion of the graph just because it doesn't have the cavity in its body, so it doesn't have a lot of sound production by itself, again, which was why you use it on an amp. And then if you graph these intensities, you can see that they kind of decline slowly, but their trends are all different. And for all of the notes A, G, and E, none of the graphs look the same for each of the guitars, which is affected by what it's made of, its composition, its shape, and its size. So another thing that has an effect on timbre is actually time. So time after strumming. And we all know that a note is going to get quieter after a certain amount of time, but not only does the amplitude or volume get smaller, the actual waveform changes too. And so these were taken 1 second apart. This is the A2 note on the acoustic guitar. And if you use the formula that we learned in class, that energy is equal to half times the amplitude squared, and you approximate that the second waveform at 1 second later is about half the amplitude of the first one, you can see that 1/2 squared is going to be 1/4. So only 1 second later, the wave has about 1/4 of the original energy that it originally had. So if you take these two waveforms and you plot their spectra, you'll actually see that over time, the higher harmonics start to diminish. So in the first spectra, there's a lot of higher harmonics at the higher frequencies, and in the second spectra, which is the waveform of 1 second later, most of those harmonics have actually disappeared and they've diminished. This is because higher frequencies tend to carry less energy overall, and this applies not only to fundamental frequencies but also to the harmonics. So over time, as you lose these higher harmonics and you get more of the initial ones, you actually approach a purer tone, which is why when a note is played quieter or when it gets quieter, you'll hear more of that fundamental frequency. The sound of the note, how it sounds, is going to be different depending on how long it's been since you played the note, whether it's a couple milliseconds or a couple seconds. So overall, Since we have all of these various combinations of the amplitudes of each harmonic, you get an infinite amount of combinations, and this allows for many different sounds with many different timbres. And the reason for all of these different combinations of harmonics can depend on the material of the instrument, the shape of the instrument, and how it allows sound to travel within it or away from it, and the depth of the instrument, as we saw with the classical guitar and the acoustic guitars, and also what type of system it is. So this project only covered a closed system, which would be the string on a guitar, but other systems such as open-closed, like a clarinet or a saxophone, are going to produce different combinations of harmonics, and their harmonics are going to be different integer values of the fundamental frequency. These are going to affect how the waveform looks and then overall how we hear that sound. And that is why we can tell the difference between different sounds.